Chi-square goodness of fit test. We want to see if a distribution is looking like what we expected. Let's suppose we have a die, and if you have a regular six-sided die, it should be uniform discrete distribution. The probability distribution would look like this. But let's suppose somebody says, hey, this die that we've been using, I think it's loaded. I don't know if we smelled alcohol on its breath or whatever, but we suspect the die is loaded, so we're going to test it to see if it is. Well, we're going to run a chi-square goodness of fit test on the distribution of the outcomes from a particular die. The null will be that the distribution is uniform. The alternative is the distribution is not uniform. So there's two of our first steps for a hypothesis test. The next step is we've got to address the assumptions, the conditions necessary to trust our results. The data, this time instead of the data just being randomly generated, we can actually use data from entire populations. So that's a little different from some of the other tests. And then these two deal with the expected counts. All the expected counts in the cells have to be at least one or more, and at most 20% of the expected counts can be less than 5. So what we're looking at right here is we are expecting that each number, 1 through 6, is going to come up an even number of times depending on how many times we roll the die. Let's suppose that we were going to roll the die 60 times and we'll see what kind of results we would get. Well, we would expect that 1/6 of the rolls will end up in each of these cells. So our expected count is 1/6 of 60. We would expect to get 10 of each number in a sample of size 60. All of these expected counts are at least 1, and obviously none of them are less than 5, so we're good. Just a quick little thing, if you're wondering why the expected counts can't be less than 1, if you had an expected count in one cell minus, observed count of 1 in a cell, and the expected count was like 0.1, you'd subtract these, you'd subtract and then square, and then divide it by 0.1. So this is going to be 0.9 squared, which is 0.81, divided by 0.1. This cell alone would give you a count of 8.1. And we've seen that even if you have like just 3 degrees of freedom, a chi-squared test statistic of 7.8 is enough to be significant. So it's because we don't want to end up dividing by a number that's less than 1 that we can't allow any of the expected counts to be below 1. If that makes sense, fine. If not, memorize those. So this is where we're at. Let's suppose we did roll this die, and by golly, it looks like that die is loaded. A lot of 6s coming up, so we follow our test statistic. Remember from the introductory thing, or you might have seen this in class, that the test statistic is the summation of each observed score minus the expected count, I should say, in the cell, squared divided by the expected count. So first cell, 5 minus 10 squared to get rid of negatives, divide by the expected count. Do that in every cell, and then we want to get our chi-square test statistic, our p-value. The degrees of freedom for a goodness of fit test is count up the number of cells, subtract 1. So in this case, we get 5. And our critical chi-squared that would have 95% below it and 5% above it, just due to random chance when the null is true and the die was really fair, it would be 11.07. So if these observed counts differ enough so that our test statistic is more than 11.07, we won't attribute those differences as being to chance and the die being okay. We're going to say the evidence suggests that this die is not uniformly distributed. Well, we can go to our calculator, the handy dandy TI A4, and we can go into our list. So we go stat edit, and we can put our observed counts in list 1 and the expected counts in list 2. And then we can go to the calculator and run the chi-squared goodness of fit test, not just the chi-squared test, but the goodness of fit test. All we have to do is say, yep, our observed counts are in list 1, expected counts are in list 2. We'll put the degrees of freedom here, which is 5. And we'll go calculate this Hummer, and we get, whoa, a really big chi-squared test statistic. And don't be shocked. This can happen a lot in chi-squared tests. You can get chi-squared test statistics that are over 100. The p-value is really small. It's to the -6 power, so it's very small. So we would reject the null. Because the probability of a type 1 error is less than 0.05, we reject the null. The evidence suggests that the distribution is not as expected. In other words, that it is not a uniform distribution. Now, suppose the dude that suggested that the die was loaded said, you know what, here's my prediction. I predict that A 1, a 3, a 4, and a 5 will all be rolled the same proportion of times with the same ratio, but the 2s will come up twice as often as the others, and the 6s will come up 3 times as often. And we might ask this person, how do you know this about this loaded die? The guy says, I don't want to say. I plead the 5th. But at any rate, we roll the dice again, and now here's what happens. These are the observed counts. We'll use the same ones that we did from that last sample. But what we need to do now is, if we know going in that we're going to take a sample of 60, then the way that we work with this information, the null, we always assume the null is true, and that the distribution would have a ratio of 1 to 2 to 1 to 1 to 1 to 3, so that the 6s will be 3 times as likely as the others, and the 2s will be twice as likely as these others. So think of this as parts. We'd have X parts in the first cell, 2 times as much in the second one, X in the third, fourth, and fifth, and 3 times as many parts in the sixth cell. So if we add up all these parts, then we need to have 9 parts, 9 X quantities altogether, and that would have to equal 60. So that means, oh, our expected counts, well, let's see, if 9x equals 60, and we divide by 9 on both sides, we would get that each X, each part, like these, would have 1 part each, would be this divided by this, which is 6.67. That's how we get our expected counts. So all the ones with 1 part, with just a ratio of 1, or you know what I mean, all those ones, you're going to get expected counts as 6.67. But the 2s are in a ratio of 2 to 1 compared to the others, so they get 2 of these parts, so 2x, so 2 times that is 13.33. This occurs 3 times as often, so that's 3 parts. 3 times this is 20. So there we go. There are the expected counts. Here's the observed counts. Once again, we show our work. The chi-squared test statistic is each observed count minus the expected squared. Add them all up. In this case, what we get is a chi-squared value of 4.698. Not a very big p-value, because with 5 degrees of freedom, we'd actually have an 11.07. Okay, that's an 11.07 as our critical chi-squared value, meaning that 5% of the time, due to random chance, when the null was true, we would get a chi-squared statistic of over 11. We only have a statistic down here of 4.68, so our result is somewhere right about there. So we didn't get a very unusual result. There's no reason to doubt the null, so we failed to reject the null. The p-value, or probably the type 1 error, is way up at 45%. We failed to reject the null. The evidence fails to suggest that the distribution is anything other than that right there.